Hello everyone. From today onwards, we are starting a new series known as Machine Learning from Scratch. Here we'll be implementing some machine learning problems from scratch using Python, only some basic libraries, and we'll also be solving some real problems using a Kaggle dataset on them. So in the first videos, we are starting off with linear regression. It is one of the most basic algorithms when it comes to machine learning. However, being such a basic algorithm, it is still very commonly used in problems and also works as a foundation for various advanced algorithms or some intermediate algorithms that help us solve some problems such as lasso or ridge regression. So today, we'll be focusing on linear regression. First, we'll be discussing off with the theoretical minimums to understand linear regression, but we'll try to understand most of it using the code itself and how we can practically implement it on a real world problem. So let's get started with the theoretical minimum. So to understand linear regression, let's start off by understanding what does it really do. So when we have a data set, let's represent a 2D data set right now, which maps one-on-one features where we only have a one feature and one label. Now, in such a case, if we have data points like this with some correlation, the dots are not very clear. Let's use this. So if we have some data set like this, which has some correlation in it, and we want to plot a line between them, we want to generalize it a bit, we can form a regression line like this from eyeballing it, right? So this will be our regression line. So this is exactly what we do in linear regression. And when we have more than one features, the line first converts into a plane when it comes to two features and a single output. And when we have more than two features, we have to solve the equation of a hyperplane. So from our basic high school mathematics, we know that the equation of a line looks something like this. Y is equal to mx plus c. So linear regression comes under the branch of parameterized algorithms in terms of machine learning, where we try to generalize the algorithm or the equation that we are trying to generalize in terms of some parameters, and we try to figure out those parameters. So in linear regression, the parameters that we have are m and c, where m is our slope and c is the bias term. When it comes to the equation of a hyperplane, when we have more than one features, the equation becomes y is equal to m1x1 plus m2x2 and so on. And finally, we'll have our bias term, which is C. So to solve this, we have various methods available, but the method that we are going to use in this video is called ordinary least squares. So it is one of the most common methods that is used to solve linear regression. It is a very fast method and also gives us the theoretical minimum of the value, which is our global minimum. There are multiple methods when it comes to solving linear regression. And if we take the example from this 2D data, we can understand that what we're trying to do is we're trying to minimize the error between the y predicted and the y on the line. So the y on the line is our y predicted and this is our y real. So we are trying to minimize the distance between them for particular x values. So, and instead of using the direct distance, we use distance square, which is our squared error. And we use this because it is mathematically more stable when compared to the absolute values. And we can't directly use the value because it will cancel out each other, because as you can see, the distance between these is negative and the distance between the actual and the predicted in this one is positive. So the errors will cancel out each other, so we can't use them directly. We can't use absolute values because it is not a continuous function, and the uh, graph looks something like this, which is not continuous at 0. There is a sharp turn in it. And when it comes to the square values, the graph is much more cleaner, and therefore it provides mathematically more stability. And then the question arises, why can't we use things like x square and stuff, right? Well, we can use x to the power 4th and stuff, but why to work with hyperbola when you can easily work with parabola? That's the motto. So after understanding our cost function and our equation for a linear regression, we'll try to represent this in a different form, in a matrix form to be more specific, so that we can apply ordinary least squares method to it. So basically, what we do is we represent each of our data set, which is this one, each instance as such like this. This is our training data. So the first instance looks something like b1 x11 plus b2 x22 x12 and so on. And finally, for the bias term, we can represent here, which is b0. We could have also used C, but this is what is more generally used in the community, and such that we can represent all of our instances in this form, right? So this is our training data, which can be represented in this form. So to represent this training data in a matrix form, we can use a general equation, which looks like this. So we have our set of B's here. So B0, B1, B2, and so on. And we have our various instances here. So those instances will be, so This v value we are not aware of right now. This is unknown. This is the unknown we are trying to find. These are the parameters, right? So the b's are unknown, and in our training data it is somewhat like this. So the first column that we have is of ones, because we want to introduce the bias term. So after that we have our instances, which is x11, x12, and so on till the number of features that we have, and so on for the other instances that are available to us. Now, after representing it like this, we can say that this matrix multiplication gives us the metrics are multiplied in a row column format that we both understand. So this row, this particular row, will go on and be multiplied by this column, which will give us a dot product between them, which will give us exactly this equation that we have written over here. So this will output the first row, which is our y1, and so on for each of the instances. So to represent this in short, we can write it like y is equal to xb, right? Where yx has an additional column in the first index, which is for our bias term, which is in the b matrix, right? So after understanding this equation, we can say that what we are trying to minimize is the difference between them, because after we have a parameterized equation, they will not be exactly the same, right? Because we are saying that the data is not directly correlated. If the data is directly correlated, then this equation will hold for a set of parameters. But if the data is not exactly correlated, but there is some correlation, as we can see in this graph, then the data will be not exactly, and there will be an error between the y actual and our predicted value, which is xb, which includes our bias term, right? So this is the error. Now, from what we have understood till now, from the cost function that we visualized here, we can understand that what we are trying to minimize is our error squared, right? The sum of error squared for each of the instances from I is equal to 1 to n, for whatever much instances we have. So to minimize this, what we can do is this sum can be represented, we can represent this sum as epsilon, uh, like the errors transpose, this dash is representing matrix transpose here, and multiplied by the matrix itself. So it will look something like this. So we have error for our first instance, error for our second instance, and so on. And then we have our the same error in a column format. So when we multiply them, when we matrix multiply them, so it will again happen in a row versus column format. So basically the output of this would be a single scalar, which will be e1 square plus e2 square, which is exactly the term we want. This is what we want to minimize. So to minimize this, we know that in terms of mathematics, from basic mathematics, minimums exist at the value where the derivative is equal to 0, right? So we want the minimum of this, which will exist at the point where the derivative of this equation is equal to 0. Now, how can we represent e dash and e? So we have already seen here that e can be represented as y minus xb. So let's do that. Make it a little bit more bigger. There you go. So our e dash e can be represented as x minus y, x b minus y transposed into xb minus y, right? Could be the other way around. The sign really doesn't matter because we are using square terms. So this is our equation. So let's open this up. So when we try to open this, it will be b dash x dash. As we know that when we are transposing multiplication, the multiplication gets inversed, and minus y dash multiplied by xb minus y. So when we open this equation, we'll get multiply these terms together. So this will give us b dash x b. Then we multiply the transpose term with y. So minus y b dash x dash, and again this one minus y dash xb. So, and the last term would be minus plus y dash y. So when we differentiate this term with respect to b, which is our only unknown, we will figure out that this value after derivation with respect to b will give us 2 x dash xb because of this value, as the b dash and b here get squared. So that will give us 2x dash xb, and this term will get cancelled out because there is no b in it, and these two terms will yield the same result. So when we differentiate them with respect to b, so here the b will be gone and here also the b will be gone, and yx dash minus y dash x, so we can represent it as minus 2x dash y, right? And this term should be equal to 0 when we are trying to find the minimum. So this equation would solve and give us that b should be equal to x dash y into the inverse of x dash x inverse, right? And we should actually do it the other way around. So x dash x inverse into x dash y. So this is our b. So after understanding the theoretical minimum of linear regression, I know it was not as short as I sought out to be, but I hope the maths made sense, and now you are able to visualize what linear regression actually does in the background. So this method as a whole is known as the ordinary least squares method, as I mentioned earlier. So I hope this made sense. And now let's get started with the code. So let's open Visual Studio. As I said earlier, we'll be just using some basic libraries to do this. Let's first implement linear regression.py. We might be also using some utility functions to implement this algorithm. So I'll also implement utils.py, and let's just get started with it. So let's talk about the dataset we are going to be using for this video. So the dataset we are using is available on Kaggle, and this is our dataset. This is a real estate price prediction dataset for regression analysis. And so we have downloaded the CSV file from here. We have not done any changes to it right now. So let's get into it and let's try to understand our data. So this is our CSV file. So we have, this is the serial number, and we have 7 other columns with that, which is the transition date, house age, distance to the nearest MRT station, number of convenience stores, latitude, longitude, and finally we have our label, which is the Y house price of unit area. So to solve this, what we have to do is, first of all, we have to import our CSV file. So we'll use Python CSV module. We are not even using pandas because all this also has a lot of abstraction, which doesn't let us understand how the data is finally being processed. So we'll import CSV. We'll use open our file name, which is real estate.csv sf, and we'll just do csv.reader our data temp data is equal to csv.reader file, where I don't think we need to do any of that. So we'll form another list here, which is our data, and we'll also import numpy right now because we'll be using numpy a lot, and we'll be converting all of our data as a numpy array. So this is our list, and for that, for row in temp data, we'll do data.append temp data, and this should finally give us our data, and we'll convert it as a numpy array. Let's print it out and let's see if what we have written till now works, which is our data importing code. So let me clear this and let me run Python linear regression.py. Okay, so we have a csv.reader object in here. We don't. Oh, okay, because I've appended temp data. We need to append the row. Yes, silly mistake. Let's do it again. And here we have it. So we have, in the first row is our header, and all the other rows are the dataset. So we don't need the first row basically. So it will just be used for column reference. So I'll say columns is equal to data 0, which is our first row, and we'll just say data is equal to data, and we'll skip the first row. So now if I print it, so I can say print columns and print data, and it should work in the exact same way, but we have 2 other lists now. Cool. So now we have the column separated, and we have our data as a numpy array. Now, one more thing that we want to do while converting it into a numpy array is to convert it into float type. I think we should do that. So we should have converted this later, and we have our columns, and after that we can do np.array our data, and we'll convert all of this as a float 64. d type is equal to np dot float 4. We can also work with float 32, but it's fine. We can work with higher precision because again, this data set is not that large that we need to worry about too much about the memory and efficiency and stuff. So we can work with high precisions. It will not take much of our time. So now we have our data set imported. Now we can print data and we will see that all of the data would be converted into float 64 type because as you can see right now it is in strings. So let's do that. And there you go. Now the data is float 64. It is represented in a scientific notation, but it's fine. That's what NumPy does. So great. Now we have our data. Now what we want to do is we first want to scale the data. That is one of our standard procedures. So to scale the data, let me make a utility function called StandardScaler as it is called that generally. So we'll say, let's define a function called StandardScaler. It will take in input as a data. And what it will do is data is equal to, so first of all, we need to find the mean for all of the columns. So we'll say column means is equal to, so the basic formula for StandardScaler, as you might be aware of it, is our data, original data minus the mean of that data divided by the standard deviation of the data. So for each of the columns, right? So if we have to implement this for each of the columns, so we'll find the column means, which we can do using now np.mean, and we'll give in our data, and we'll say the axis is equal to 0, which will calculate for each of the means, and we'll also calculate columns standard deviations, which is equal to np.std data comma x is equal to 0, very similar code, and we'll say for data in, for row in data, row is equal to row minus equal to means, row means, and row divide equal to OLS. And rather than doing it like this, we should do it like this to affect it. I data I minus equal to calls and data I minus equal to code standard deviation. And okay, so what we are doing right now is converting the data in place. So I don't think it is a good idea to convert the data in place. So what we should rather do is make a new data, which is the copy of this. I think that works. Right? Yeah, I think it should work. And we'll say new data is equal to this. And here we'll go on with that. And we'll just say new data. And we'll return new data. We could have done that in place too, but I say if we are using a Jupyter notebook and stuff and we run the same column again and again, we are implementing the standard scale, it will rescale the values over and over again. And I'm not sure if that would bring any differences to the data set, but again, that could cause some difficulties in future, and we just want to implement this once per data. So I think this should just be fine. This should work. So this is our utility. So we'll import our standard scaler from the utility functions. From utility import standard scaler, and we'll implement that after we have split our data set into x and y. So our x will be data, all the rows, we want all of the rows in the x, but we only want the first 7 columns, right? So there's that, and after that we want the 8th column to be our y. So let's print this out. Let's check if this is correct or not. We'll do it right below it to make sure. Okay, we have error x index 7. Oh, okay, sorry. So we should have x7 here. And this is working. So this is definitely the price values. As we looked at the data set, you can check it out yourself. And this is our feature. So we should have 7 features per value. Okay, we'll not be able to see that, but we can do that with the help of dot shape. So this will give us the whole picture. Again, so we have 7 features in the data labels. These are our features. Now, one more thing that we have to understand is that the first feature that we have in our data was the index, right? So what we have to do is we don't want to include the first column too. So we basically have 6 features because we don't want index to be one of the features. So that works. Now we don't have the index values in this, and that's great. So now we have our x and y. Okay. So now that we have our data split it into x's and y's, and we have also removed the index features, and we have it in our numpy.arrays as data type np.float64, and we also have an implementation of a standard scaler. We first want to be able to split the data sets into a train and test split because that's what we want to use finally. So to do that, what we can easily do is we can define train test split here, which will take in x and y and the test size. We'll consider that shuffle is always true, and we'll keep the default value to the test size as 0.2. And to do this kind of probability thing, we'll also import the random module. So import random, right? So we'll say if random.uniform, which will output a value between 0 and 1, both included, is less than test size. So we want to have two indexes here, basically. So the two indexes will be our test indices and our train indices. And for I in range len x, we can do it for any of them like this. So for I in range len x, we will have if random.uniform 0 to 1 is less than test size, so we want that to be inside the test size, test indexes dot append I, else train indices dot append I. And after that, finally, we'll also form a random permutation of them. So we'll just say test indices is equal to np dot random dot permutation of test indices, and same for the train indices. And finally, we'll output our x train indices, our y train indices, our x test indices, and finally our y test indices. That would be in our return statement. So this should work. This is our train test split. Let's check it out. So let's import it here from the utils. Train test split, and we'll say x train comma y train comma x test comma y test is equal to train test split x comma y comma test size. We'll keep it 0.2, so let's leave it at default for now. So we have exactly what we wanted. We have splitted the data set into a 20% split. So we have 336,6 here, and we have 366 test sizes. So all of this is working correctly. We can understand from the shapes themselves. So great, this code is working, and we also have a shuffle there. So we can also keep shuffle as a parameter if we really don't want to shuffle it for a particular instance. We mostly have to. So I'm by default keeping it as true, and we can just say if shuffle is equal to true, then you have to do this, otherwise you don't. So that's fine. You can do that if you very particularly want to do it without shuffle. You will not really want to do it most of the times, but we can have that too. So after we have our train and test split, we want to scale our training values using our standard scaler. So we'll do that. So that will scale our train values. Now we have to implement our train function. So let's see. So let's define our train function. The train function will take input as x and y values. So what we have to do in the train function is that we basically want to implement the equation that we discussed before during the theoretical aspects, and this was our final equation, and I hope you understand the derivation of it, which is not really essential, but it gives you a holistic approach and gives you an idea that what we are trying to minimize when it comes to linear regression and how do we end up doing that using mathematics. So now let's define our train function. So to do that, we'll first have to find the mean. For we don't necessarily need mean, but what we're doing is our first value, which is the np.linear algorithm dot inverse of, so this is x transpose x transpose x x transpose x np dot inverse, so np dot linear algorithm inverse of np dot x dot t and x, capital X. So this is this term, and for the term where xt into y, we'll just do np dot x dot t comma y, and we'll return our dot product of both of these as our final b. We'll say return np dot xt x inverse comma xty. So this is our basic training loop. This is not even a loop when it comes to this one, because we are solving it using numerical methods. We are not solving it analytically and optimization algorithms. So that makes it pretty easier because it is much faster and will ensure us to always give the most optimum value that there is. And except when compared to gradient descent and stuff, where we have to implement the learning rate, and the learning rate can be slightly high, where it can jump off from the most optimum values a little bit, and it is very difficult to stop at the least at the actual minimum. So that's great. That's the advantage of ordinary least squares. So I'll mention it here, ordinary least squares method. So after we have done that, we can basically, what we can do is now that we'll be returned with the weights and biases when I do train x train comma y train. Now great. So now we have our weights and biases. Now to make a prediction, we can also define a prediction right here, which is fine. So if you want to predict something, what we can do is we can input our weights and biases and our x test that we want to predict. Or we can just write x new. So to predict this, what we have to do is we'll have to basically our y output. One more thing that we are missing right now is our bias term. So we have not added an extra column in the x train of ones that we need. So what we can do is first implement that so that we have the bias term when we learn something. So to do that, what we have to do is, okay, so let's add a function in our utility function itself. So it will be called as add bias. Right, so add bias will take in our data that we want to add the bias to. So to do that, what we'll do is basically just say that data, let's form again a new data so that we don't alter with the first one, and new data dot new data is equal to np dot c. This is a basic function that is used to add an additional column to our data. So we have to add an additional column. So that's in our new data, and the column is np dot ones of the size len data. Right. So this makes sense, and we'll return our new data. So this should work, and let's test it out right here. We will have to import it first. So add bias, and we'll say add bias x. Right, that's all we have to do. So let's print add x before we add a bias to it, and let's print x after we add a bias to it. So we'll be able to see the difference. And here you go. So okay, we have not implemented this yet, and let's say pass for now. Let's see. The class is not callable. Oh right. So our mistake is that we are using the parenthesis, except the np.c methods utilizes the square brackets. So that's something to remember. So let's run this again. And there we go. So we now have our data, and in the last column we should have ones. So you can see it is again representing in scientific notations, but we can see that the last column of our data has now ones in it. Before it used to have different values in it. So we should actually do that after scaling it to make more sense, but it's fine. You can do it any other way, because for if we just have a columns of ones, the mean would also be 1 and the standard deviation would be 0. So yeah, I think that can cause some errors. So great. So we'll implement this after scaling the output. And so our x train will have biases now. So now we have a bias term which is in the last column. So what we have to do is we'll have our weights. Our weights will be in weights and biases, all columns, all columns. Right. So what we want from this one is we want the weights and biases for all the columns except the last one. So this is what we're going to do, and our bias will be equal to weights and biases, and we'll include the last one. So, and to predict a new value, what we'll do is we'll just say return np dot x new comma weight plus bias. So now we have our implementation for our predict. Now we can get our weights and biases using the train, and after we have trained it, we can just basically predict for our x test. So we'll do y predicted is equal to x test. So predict weights and biases, comma, x test. This should give me y predicted. Let's print out the y predicted. Okay, so we do have an error. Oh, okay, so this is our error. We need to pass in the train in it. Now it is working. So now we have our predicted values. So to test it, we'll use the mean squared error. So let's have our implementation for that going on here. So say MSC, and we have y actual, comma, y predicted. So we'll say the mean squared error will be, so we'll just do for I range y actual, and we'll also assert that len y actual should be equal to len y predicted. Otherwise, we'll just output that the length of compare and predicted. So for I in range y actual, we'll just say len y actual. We'll just do sum. We'll have total sum. Sum plus equal to y predicted minus y actual square, and we'll also at the end of it, what we'll do is we'll just do total sum divide equal to len of y actual. So this should so this should give us the mean squared error. Great, and we'll just return the total sum. Okay, so let's calculate the mean squared error for our values. So print mean squared error for y predicted or y test. Now again, we have not imported it from the utils, so let's quickly do that. Now I'm making this utils file here because I think in the many of the functions that we'll be implementing in the features, we'll have to re-implement the mean squared error, standard scaling, TrainTestSplit. So these are all of the functions that we may have to implement for other algorithms as well in the series. So that's why I'm making a utils file for them. And yeah, I prefer that you watch the series in a sequential manner so that we can build up upon the concepts that we have discussed in the previous videos. So this video has had a lot more theoretical detail in it, but as we follow up, we'll try to focus more on the coding part, as the other algorithms will just be a slight build up upon these algorithms itself, and they will just have some coding tricks in it to make them better, to make them perform better mathematically, practically, all of those stuffs. Great. So let's see what is the mean squared error. Okay, that's not great. That's not what I wanted to print. Did I not save this? I predicted minus one. Okay, so what I'm doing is I'm not doing this. Now it should work. Okay, so that doesn't look right. So we found the error. So basically the error was, I think most of you must have figured out that by yourself, you are not scaling the X test. So we need to do that before we do anything. So we'll implement the standard scaler on Y test. And okay, so one more thing that I want to highlight here is that we should have also outputted the mean and the standard deviation from the X train itself, because when we are trying to standard scale using our testing value, we want to use the mean and standard deviation values from the train data set. So we'll have to implement that. So what we can do is we can make it output the call mean and call std also, and we'll ask if train is equal to true. So those are the two things that we'll add there. So let's quickly go in there and add these things. So if train is equal to true, so let's write it here. There you go. So train, which will be by default be equal to true. So that means if the train is equal to true, you need to calculate the call dot means. So if train, need to calculate these. Otherwise, you can just use our call mean and call STDs. Standard deviations. STDs doesn't sound that good. Or we can just do it like this. So our parameters by default it will be an empty list, and we don't need to use the train. We just need to use if train is empty, then you will have to calculate this. Else you just say goal means equal to train 0 and goal std equal to train 1. And also one more thing we can do is one more thing that we can add here is to just output the goal means in goal std. So that should work. This should be fine. What we'll do is just assert that len train equal to 0. Else we'll just say couldn't comprehend the mean and key values from the list. Okay, so that should work great. That should be fine. So here the len will be 0, so it will work the same way. We don't need to use len train is equal to true with the deco. So there it is. Let's change this, and here it will be outputting the call mean and standard deviation in the correct order, I hope. Call means and call standard deviation. So now we can just say that when we are scaling the test one, we'll just say train is equal to call mean comma call std. So what we will do is basically use the column means and input it that is used during the training and change the whole data on the basis of that. So we did it in a very do not repeat yourself method, which is what we want to do, the try method of coding. So this should work. So now we are standard scaling the X test, and then we are trying to predict it. So let's run this again. Okay, we get an error. Great. What's the error? Oh, okay, I get it. So it is always outputting this. So the call means and call standard deviations. So we don't want it to necessarily do that. So we can do it like that only. So would be the best way of doing it. Let's just simply implement a clean way of doing it now, and we can change it further later. So if len train is equal to 0, then we have to do this. Else you need to return just the new data. So now it should work. Great. So now we have an error of 74.103. That's the mean squared error. So basically the error might be somewhere between, like in terms of the, okay, so what was the mean value for our y column? So y train, let's do that. Print mean np dot mean of y train. So, and let's use the square root of this. I think it's in the math library. So let's import math by Python. Great. So now it will be in the same range, in the same unit as our y train. Okay, so the mean value for y train is 37 and the mean error is 11. So that's fine, I guess. It's not the world's best model, but we were just assuming that all of the features now are linearly dependent on the output. So that was one of the big assumptions that we are making right now, and this is a very standard and one of the most basic algorithms, and it is able to give us some form of a decent results. As you can see, it is able to give us the error in terms of 7.86, which is decent. So you can understand that for that is 1/5, so you can reach pretty close to it. You have a 20% error rate in your output, but that still works fine. So we have an implementation for it. One more thing that I like to do is to make it more in the scikit-learn format. Let's implement a class here. So let's call a class as a linear regression. This is just a bit of, refactoring of the code just to make it a little bit more cleaner and more usable in some standard situations. So we'll just implement a class of linear regression, and here we'll have, first of all, our defining init value, and in the init we can just define it like self. We don't need any input values basically. So our self.model would be equal to an empty list in the start, and what would happen is let's call in these. There will go our self, and except of returning this, now we'll say self.model is equal to this. So we are changing that value, and if we are predicting something, we'll just say, instead of passing in the weights and biases, we can directly use our self.model So instead of this, will be self.model, and we'll do one more thing to make it work. We'll just say assert len model, then self.model is greater than 0, else you will print output use the train function first to obtain the parameters before predict. So that should make it more convenient to use. Now, other than that, we can also add some more functionalities, and let's refactor the code a little bit here too. So we'll just do here, we'll say just in a very scikit-learn format, we can just say our regressor is equal to linear regression, and that will open an instance of it. After making an instance, we'll just say linear our regressor dot train this, and then we do this, and we can just say regressor dot predict, and we don't need to pass in the weights and biases anymore. We can just pass in the x test, and these are the basic 3 lines that will implement our code now. And here this becomes our root mean squared error now. Root mean squared error, which gives us the output in the same unit as our data. So that makes the error much more readable for ourselves, because the square of this would be around 50, and we'll be thinking that okay, so the mean value for y is somewhere around 38, and the output has an error rate of 50, which is much higher, but actually it is not, because it is in the square term. So it is somewhere around 7, so which is around 20%. We can also calculate it just to make sure what is the error rate. By implementing such a simple algorithm, we are able to achieve error rate of somewhere around, like, what would this be, right? 7 divided by 38 into 100. So yeah, around 18% error rate, which is decent for such a simple algorithm, and we were able to code it from scratch. We didn't use Kaggle, we didn't use pandas, we didn't use much of the external libraries. One of the only external libraries that we used is numpy, and we had to use numpy just to make these linear algebra implementations easier for us. Otherwise, we'll have to work a lot through them, and also the calculations that we have directly done here in the matrices, assuming that they will be done element wise, is with the help of numpy arrays only. Otherwise, if we have implemented it using a list, the lists don't behave in an element wise fashion in Python, so that would have caused some errors. So all of the other libraries that we have used in this implementation are the Python default libraries, which is great, and that is working. Now, one more feature that I want to add, which is an optional feature, is just to import pickle, and we can save our model. So let's define a new functionality, which is def save. This will just need the self, and we'll also need the file name. So let's import OS now. And we'll just say if os.path.exist file name, then it will ask the user if you really want to change that. So it will say change is input file with similar name. So this will be our input, and we'll just basically say if change dot lower is equal to y, then open with open file name as write binary as f, and pickle.dump, and first we'll pass in our object, which is our self.model, and then we'll pass in our file name, not file name, just f. So that will pickle.dump for us, and in the other situation we'll just return, we'll just skip everything, and else if os.path the file name doesn't exist, we'll simply do this. So yeah, so this should work. This makes sense to me. So if os.path exists, it will ask us if we want to overwrite it or not, and if we say we want to overwrite it, it will change it for us. And if we say we don't want to overwrite it, let's also have a backslash in here just to make it much more convenient for us, or just add it like this. So it will pick a dot dump, and we'll just say print saving the file model, and here also we'll say print saving the model. And let's also have a loading function. So load self comma file name again, and we'll just say assert os.path.exists file name. If it doesn't exist, it will just say the file to be loaded doesn't exist. And for the loading loop, we'll just do the same thing. So we'll say self.model is equal to pickle.load. Pickle is basically a Python standard way of indexing everything and writing it as a binary. So we'll just say pickle.load, and first we'll have to read the file. So we'll say with open file name, comma read binary as if, and we'll just say self.model is equal to pickle.load, and we'll load in a file. So that's it. That's the code for saving. So now it is much closer to the scikit-learn implementation, and we'll say we have reduced the error, and this was the ordinary least square method of implementing linear regression. We can just quickly check this out. So we'll say when we have trained the model, we'll save it. Let's just say if os.path.exists, and we'll write in our, so let's say model.pickle linear regression as state.pickle. Then we'll say file already exists, trained model exists, so loading the model, and we'll just do regressor.load, and we'll input the our file name to this, and we'll input the file name here, and we'll say regressor.load file name. That should work. And if it doesn't exist, we'll just say training the model, and after the model has been trained, we'll regressor.save with the same file name. So that's how you can use the saving and loading using a pickle file, which is a Python standard way of storing any object, any Python object, in a binary format. So that should work now. This is our pickle. This is our linear regression class, and everything is in there. And we can just simply do all of the operations like this. So this refactoring, I think, has worked great. We also have the utility functions with us now. So let's run it once again just to check it out. Let me exit the Python terminal, clear the terminal, and we'll say linear. Boom, saving the model. Now we have the model like this. Now this is our pickle file. I'll open it in a text editor. It is basically in the binary format, so it will not be much readable, but you can still see that it is a numpy core multi-array, which is a numpy ND array, and you can understand that the data type is float 8, and then there are just the numbers stored in it in the binary format or some other format. Maybe it looks like hexadecimal format, but I'm not sure. So it's just their way of indexing it. So that works. It must be stored in a hash format, I think, so that's why it is not interpretable. And now we can also, if we run this again, it will just work because the loaded model exists. So, but why didn't it? Oh, okay, great. I've not even printed this out. So let's print this out. Boom, train model exists. So loading the model, and it just works. Now you are able to see some of the differences here, and you must be thinking that we have a trained model, so why we are getting a different error every time? That's just because that the data is always changing, so the data is shuffled and it is randomized. That what index we are gonna input to make the train test split here. So that's why there are some changes in the error because the X test keep on changing. So that's fine, that doesn't matter. I hope this implementation made sense to you. Now most of you during this whole code must have been thinking about, why are we not implementing linear regression using gradient descent? Well, it is one of the methods to implement linear regression, but here we have showcased ordinary least squares method because it is one of the most common methods that is used to train a linear regression, and it is what scikit-learn uses most of the times. Gradient descent is used when the dataset is too large, has a large number of features, or we want to use a regularization term and introduce some new forms of regression, which are our lasso and ridge regression. That's when gradient descent makes its impact. Otherwise, this method, as you must have been able to observe the advantages of it, that We don't have to worry about anything. Like we are always going to get the best values. We don't have to set any hyperparameter by such learning rate and stuff. So this works great. But when we want to implement regularization terms and we have a large number of features and a large rows in our data set, a large number of instances, that's when the use of linear regression with gradient descent becomes important. And then we can introduce the L1 and 2 DOM, and then we can implement ridge and lasso regression. So that's what we're going to be doing in the next video. This video ends here. I hope the implementation made sense to you. I'll upload all of this code in GitHub. Bye bye. Take care.